I have to, or I can introduce our next speaker. It's Filippo Gerin from Maffei's Engineering from Italy. And as I just learned yesterday evening, he's actually a mathematician who's working as an R&D software developer. And I think he's going to give us a really exciting talk about FEM coding for insulating glass. So I'm really excited about that because I already got a short preview from you in our discussion yesterday and today. So once you're ready, the stage is yours.
Hi everybody. Today I show you our new code for the nonlinear analysis of insulated glass units. This code was entirely written from scratch at Maffei's Engineering with a joint collaboration with the University of Parma. The pressure inside the cavity in IGUs is mainly affected by three factors. The one is barometric pressure variation, second is temperature-induced variation, and the third one is load sharing. Load sharing affects heavily the behavior of the structure and causes high nonlinear behavior of the structure. When you apply the load on the upper surface, it changes the internal volume, and so you have an increase of internal pressure that transfers the load to the lower plate. Here is an example of our code, and these are the results for a case of an IGU with a concentrated load on the upper surface. And you see here the maximum the principal stress diagrams for the three glass layers. You can see here how the stress diffuses through the interlayer, and by load sharing affects highly the lower plate. To model the gas cavity, we followed our variational approach, which consists in modeling the total potential energy inside the gas cavity. And we take the first variation of the energy equation to give the equilibrium equations that are the nodal forces acting on the cavity. And these are the results of the pressure variation between atmospheric pressure and internal pressure of the cavity. We take the second variation of the energy to calculate the Hessian matrix, the stiffness matrix, which is needed for this numerical solution of the finite element problem. The term in the red box this poses significant challenges in the numerical solution because this term affects all the nodes of the cavity, and it results in a stiffness matrix which is dense. And this is a problem because finite element implementation uses sparse solvers, and so needs a sparse matrix. And we treat this term with a special technique that allows us to sparsify this term without affecting the convergence of the method. We combined the modeling of the cavity with in a solid shed model, which represents the laminated glass packages. And tomorrow I will talk more in detail about this topic, but for now it's enough to say that we use a geometrically exact strain measure that allows us to to consider the initially curved geometries of the IGU. To build the mesh for the solid shell model, which is a 3D mesh, we start by considering 2D shapes. This case is a polynomial shape. There are some holes for the hole fixings, and there are some loaded area where we want the mesh to pass here to calculate exactly the load there. And to be able to do this sort of mesh, we created the code for the mesh entirely from scratch. And this code gives a quadrilateral quasi-structured mesh with very good elements quality. And this 2D shape, then we embedded in 3D. Here we can curve the geometry with one single curvature, double curvature, and then we apply the IGU. The IGU package is constructed by extruding this 3D mesh along the normals to give the layers. Here I return back to the modeling of the gas cavity. Here is a comparison with a commercially available software, Strand 7, which is a general purpose finite element software. And here, for example, we have two options to treat the stiffness metrics for the cavity. One is the complete option, so to model the entire matrix, which, as I said, is a dense matrix, and an approximate one. The complete option gives a very good convergence of the nonlinear steps, but it's very, very slow because of that dense matrix. Instead, if you use an approximate solution, each step is it's faster, but you see the convergence is not good. And this is how Strauss compare with our software. And I consider a curved geometry with horizontal load. And this is a graph where you can see the time of the computation with respect to the number of elements in each side of the mesh. And you see here that our code is 10 to 100 times faster with respect to this commercially available software. And this is because of our special treatment of this dense part of the cavity Hessian. Here we put this code, this finite element code, into a web application, and in this web application we built it to make possible to analyze architectural glass. You can put a boundary condition, all the loads, and there is a section for the climate loads, and it runs the simulation in our servers, so it's completely online. You don't have to install anything. And after the analysis, you have the check with respect to European and American standards, and with the results of the analysis are written in a PDF file that you can download. This software is completely free and free to use for anyone, and it will will be available very soon. And so if you are interested, please check the site apps.maface.it and check for the date of release of this software. Along with the web application, we developed a Grasshopper plugin with the same functionalities of the web application, but we created these blocks to be able to make the software inside Grasshopper, so you can define your surface entirely in Grasshopper and use Grasshopper functionalities, or you can import any geometry in Rhinoceros, and then these geometries, with these geometries, you can run our code. The simulation is always done in our servers, so you could also have a low-end device, also a tablet, for example, and you have the results in 3D. It's programmable, so you can do any type of modification to these standard blocks that you can see here briefly. Again, these plugins is free and will be soon available. So let's check the same site for the release date and to be updated. Here I compare the results of the analysis with strand 7, and the first example here is of laminated IGUs with a pseudo-concentrated load on the upper side. It's a simply supported IGU, and here are some comparisons. We consider the strand 7 with X8 and X20 brick elements. And you see the mesh for 10 elements per side. And here is the results for the maximum displacement with respect to the mesh, the increase of internal pressure of the cavity, and the maximum principal stress. And you see how our code is almost matches the results of Strauss, of strand 7. Here are other diagrams. You see on the upper side the time of computing with respect to the mesh size, the mesh number of mesh elements. And you see again the y-axis is in a logarithmic scale, so our code is it's much faster, which is the red dots. And for the graphs of load versus max displacement, loads versus pressure difference, and load versus max principal stress, the results are actually the same. So our code is exactly reliable. Here's a second example with the curved IGU with the line load, and you see here the results again are very similar to that of strand 7 for maximum displacement, pressure, and maximum principal stress. You see again the time of computing, which is very low for our code, and the load versus displacement, pressure difference, maximum principal stress are very, very, very similar. And note that the pressure curve starts with a negative slope, and this is the combined effects of the curved initial geometry with the nonlinear analysis. The third example, we consider the pendulum impact test with the standard of DIN N, and this is are two tires that falls from 1 meter of height with 50 kilograms of mass. And here the it's a dynamical simulation, and so you have to take care of the loaded area of the tires. So you have to calculate the displacement of an equivalent spring mass system and calculate the load on the glass surfaces. And this is done in exactly the same way as MEPLA does. So we see the comparison, MEPLA versus ours for the maximum plate displacement and maximum principal stress. You see they are very similar. On the bottom are the stresses, the maximal principal stresses diagrams for 3 typical times. And to show you, the first one is when the pendulum is approaching the upper plate, and you see the 2 ellipses for the load on this surface. The second time is the upper surface and the bottom surfaces, maximum principal stress, and is when the stress is at its maximum point, its maximum value. The third images is when the pendulum detaches from the IGU and leaves it to freely oscillate, and you don't see the loaded area of the pendulum. We built another different stuff now. It's not a finite element, it's a neural network prediction. And we done this because many times you don't want, let's say, a grounded solution, a finite element solution, because you don't have time, or maybe you are trying some configurations. And so we use a neural network to make previews of the most common cases, for example, rectangular plate, point loads, etc. Here we see the ground truth on the left, the finite element solution for the maximum, for the stress, principal stress, and the neural network prediction. You see the results are actually very, very similar, are not perfect, but with a good enough accuracy to make some tests, some tries, and prior maybe to make the fully nonlinear finite element simulation. This also will be available in our glass software. And I make here my conclusion. We developed this software by own with the University of Parma. It treats the cavity with an approach that speeds up computations. It's faster than, for example, Strand 7, which is it's general purpose. Our software is specific. And I invite you to go to our site and to keep updated. There is you can put your mail. You'll be advised when we release the software. And thank you for your attention. And see you maybe at the stand. We have the stand on the other part here of the GPD. Thank you.